He has a book.
Yes, it's
And
an
it's
ebook.
entitled?
It's entitled Radiation Exposure and Its Treatment, and it's available on Amazon. It's an ebook only. Part of that is that AFRI has zero interest in hard copies these days. So I highly recommend it.
You should get it now so you have it available in case you are exposed to radiation. It's not, okay, anyway.
No, it's not.
Okay, so how many people were here during Don's talk this morning? Just raise your hand. Okay, so actually the large majority. Okay, Don presented his results in units of millisieverts. A millisievert is a thousandth of a sievert or a tenth of a rem. Okay, which for many people may be a more conventional unit. You may, the measurement, as I recall, was 490 millisieverts for a 220-day or something outbound cruise is what you measured. Well, why don't you review what you're finding? Well, let's start out there.
Sure.
Just briefly review the result.
Right. So I think from the relevance of human crewed missions to Mars, I think one of the things that we found was that for a 6-month mission to Mars, the radiation dose equivalent, which is the dose that impacts biologic tissues, so it includes the quality factor or the ability of the radiation to actually do damage to the tissue. We measured, extending it to a 6-month one-way trip to Mars in deep space, we measured a number of about 331 millisieverts. So a third of a sievert. A sievert's generally a canonical number that people consider as kind of the area where you want to try to stay below. So a round trip would be about 660 millisieverts just for the deep space portion of it. The other relevant number that we observed was that the contribution, that's a contribution from 2 types of radiation: galactic cosmic rays, which are these very high energy but relatively low level and slowly varying type of radiation that comes from outside the solar system. It's very difficult to shield against. And then there's these solar energetic particles which come from the sun. They're sporadic, they're hard to predict. And in the case of Curiosity's the 7 months of observations that we obtained from the Curiosity cruise to Mars, we observed 5 solar particle events, and of those, from those 5 solar particle events, about 5% of the total dose equivalent was due to these solar energetic particles. So 5% of these 330, or actually about 25, well, I'm confusing things now a little bit, but about 5% of the total dose was from solar energetic particle events. The real question is, you could go at a different time, you could have no solar particle events, you'd have a 0 contribution. That total number might be 5% less. If you go at a more difficult time, you could have 50% of your contribution from solar particle events. The contribution from the galactic cosmic rays varies over the course of a 10-year or 11-year solar cycle, and that can be a factor of 2. So the numbers vary from the time in the solar cycle and whether you're lucky or not.
Okay, and these results were taken during solar max or solar min?
These were obtained during a week solar maximum, where we basically are still kind of at the end of solar max right now. So it is solar max, but it's about half the strength of typical solar maximum.
Okay, so perhaps it's sort of an average condition.
Could be. It's not. That's something that I think, these are the first measurements of this type. We've been taking measurements in Earth orbit from the GOES spacecraft for many, many years. Heliophysics and space weather monitors record these measurements. We've been trying to take records of these measurements since the dawn of the space age. So this is the type of measurement that you really want to have a long time series of, so you can understand the variation over the solar cycle, as well as the variability that one could see from the different solar particle events.
Okay. Now, this may well be a different instrument, a different kind of instrument than Marie. However, I do recall the bottom line dose estimates coming from the Marie investigators circa 2002 from Carrie Zeitlin were in the same range as these.
That's correct. Marie's not so different, actually. It's a similar type of instrument. RAD has a more extended range. Marie could only observe up to about lithium. RAD can measure all the way up to iron, and we also measure neutral particles. Marie was designed to measure the deep space environment, so it was not inside a spacecraft shielded, and it was only in orbit for its duration of its life.
Okay. Okay. Now, I think these results are interesting, both, of course, in themselves, but also in terms of how they have been characterized by various groups of people. Because, okay, the dose measured, this measurement, 330 millisieverts, 33 rems each way, 66 rems round trip. If very comparable to the estimate of the dose produced by the Marie scientists in 2002, and if you pick up a copy, I saw someone here has a copy of the Case for Mars with you. If you'd open it up to page 131, you have it there, sir? Yes, sir. Okay, look at the bottom of the page. What are the dose estimates that were published there in 1996?
Conjunction was 52 grams, opposition was 58.4.
Right. Okay, and that was based on models that had been developed by Ben Clark, who was one of the scientists on the Viking mission, which flew in 1976. So while these are some refinement, and the instrument has a greater range, and some of these earlier estimates are based on inferences and not measurements, the bottom line answers are not dissimilar. And now here's the thing. If you, the most authoritative report that has ever been done on the biological effects of radiation is known as the Biological Effects of Ionizing Radiation, published by the National Academy of Sciences in 1972. And their estimate, which was based on something called the linear hypothesis, which we'll hear more about shortly, was that, roughly speaking, if you have a dose which is delivered over an extended period of time, which is the case here, that is, this is extended relative to the body's repair cycles, which are short and longer and up to about 60 days. So this is long compared to that. You do not get any, you don't expect to see any immediate effects from this radiation, but rather you expect to, they infer a statistical risk of cancer at some point later in life. And this is undemonstrated because with doses this low, you don't see any immediate effects. You cannot identify immediate cause and effect. But with higher doses, there is clearly a clear statistical risk. And then ratioing it down, you know, from a 10% risk with a much higher dose of like 600 rem over, okay, they get a 1% risk of a fatal cancer sometime in the next 25 years of life, based on medical technique as known in 1972. Now, so that was basically the dose that was measured here, and a 1% risk. Now, NASA, now it is true that subsequent to the BEIR report, in response to pressure from anti-nuclear people and so forth, various bureaucracies have revised down their safety limits, revised up their risk limits, and on the basis of some of this material, NASA characterized this as representing a 3% risk. Okay. And also then went on to comment that they had chosen to designate a 3% risk as too much, and therefore these doses showed that we cannot go to Mars until we have more advanced propulsion than we actually have. So I found this extremely remarkable. That is, the headlines in most of the press coverage of this, which took off from this point of view, saying, Curiosity shows radiation a deadly peril to potential Mars travelers, and so forth. And in other words, it was represented as an argument for the cannot do, the can't do spirit at NASA. And therefore, in my view, frankly demonstrated something of considerable clinical interest about some of the people at NASA headquarters. Because, as I say, the results, while more sophisticated, so forth, were consistent. They did not measure something that was 3 times the radiation dose that the Marie scientists estimated or that Ben Clark estimated. It was quite comparable. And so, to me, the RAD results were substantiation using more sophisticated techniques of the previous results, which said that radiation is not a showstopper on the way to Mars. And yes, in my view, that is their significance. But I know that Brian has written on the validity or lack thereof of the linear hypothesis itself, which, by the way, even in the BARR report, it's written there saying this is suspect because it's not clear that the risk apportions down in linear fashion. They say, we're using this because this is the most conservative hypothesis relative to safety, okay? Because after all, there are many things, if you drink a glass of wine a night for a year, there will be no ill effects. If you drink 365 glasses of wine in one night, you will die. But they did not void it. They say they were adopting it, but they themselves indicated that they felt that it was not necessarily valid. And but since then, there have been studies that substantiate those suspicions. And Brian, why don't you comment?
Sure. It's too bad I don't have I've got a really good slide on this because it's kind of hard to see to understand without seeing a graph. But basically, you've got a point up here. If this is the zero, this is the cancer rate. This is the Gray's rate, sieverts, what have you. And you've got a line going this way, and you've got a data point up here. And you linearly extrapolate. Well, you linearly extrapolate because the data is either non-existent or weak in this region. But there is reason to think that there's actually a minimum in there somewhere which is below the background level for cancer. And there's a lot of things that cause cancer. There's viruses. We know about the HPV vaccine, which is to prevent a cancer, HPV-based cancers. There's chemicals. Everybody knows about the coal tars in cigarettes. Nicotine is not particularly problematic, but other chemicals are. There's so many chemicals that cause cancer, it's kind of ridiculous. There's nutritional issues. Being low on vitamin D is correlated with somewhat increased risk of cancer. Not having enough iodine in your diet, one of the factors that's probably, well, it's a highly probable risk factor. It's a highly probable cause is lower iodine intake today for women relative to breast cancer. today it's about 50% what it was in 1950, basically because so many people think sea salt is better because because it's not iodized, which is not correct. But there's a lot of things that can cause cancer, and radiation is only one of them. The overall risk of cancer for a man in a lifetime is about 25%. That's not the risk. The risk of dying of cancer. Excuse me. The risk for a woman is about 20%. And so you've got the linear no
Threshold.
yeah, the linear no threshold model it extends this linearly as you said. It's very conservative, but there isn't evidence. It's not an evidence-based calculation. And there are some people who are extremely activist about it, and for example are taking CT scans to task based on getting publications that use the LNT model that again aren't evidence-based, but there's this kind of circular referential set of papers in this particular area. So does that cover the base for you?
Yeah, but you could also add whatever additional comments you'd like to discuss.
I can go on for a long time, probably not. But there's, like I said, there's the most probable minimum is about 20 rem, about 0.2 gray. I think in gray is supposed to be a measure of absorbed radiation as opposed to incident radiation. Whether it actually is or not is highly variable. It depends on who's doing the calculation, et cetera. One of the issues is that if you look at a spectrum chart, effects start with soft X-rays, and soft X-rays, very, very low energy X-rays, are mostly absorbed. As you get higher and higher, when you get up into gamma, you can get into the single digits in terms of percentages that are actually absorbed. Cosmic rays are extremely high energy, which means most of them are going to go right through you. So if you don't apply a correction factor for frequency or energy to your radiation detection equipment, you're going to overestimate because because you're going to catch more incident radiation with the kind of detection equipment that is used to detect gamma rays and cosmic rays than a body would necessarily absorb. But I can't tell you what that conversion factor is, for example, for these results. And I just don't know. I don't know what fraction of incident radiation is intercepted by the instrumentation, and I would have to look things up to figure out what by frequency range. But that's a general rule of thumb. Another thing to consider is that there's a wide variation, and this has been made very clear in oncology, because millions of people have had radiation doses to parts of their bodies that are 50 to 60 gray, cumulative in 6 weeks, because that's standard radiation treatment. Some people have had more. If their oncologist thinks that they, otherwise there's no chance of survival. And the same course of treatment, it's about 1.5 to 2 gray per day, per session, in about 10 to 15 minutes. These days it's in a shorter period of time. And one person may get through it and have relatively minor redness, erythema, essentially sunburn visible on the skin, and somebody else may have necrosis and skin sloughing off. and which is really hard to deal with. The factors that we know about that go into that are dietary, but also general conditioning. And an example of that is the rate of DNA repair in different people is significantly, very significantly, and probably one of the biggest factors there is your general aerobic conditioning. High-level athletes like Ironman triathletes, those kind of people, they've been looked at, and their telomeres are 10 to 15 years younger than their calendar age, which means their DNA repair rate is higher. There's a lot of things that get cranked up by that kind of physical stress. What are called heat shock proteins, which are really protein folding chaperone proteins, and other things kick into gear quite strongly. So, one person who, a person who's in excellent physical condition is going to be better off. They're going to be able to tolerate a higher radiation dose than somebody who's not. And then of course there's things like there's subpopulation. There's a very small fraction of people who don't tolerate high-level aerobic exercise very well. They don't adapt to it. It's possible that those people may have may not be able to turn on the genes that regulate the heat shock proteins and DNA repair the way others do. It also it raises your level of catalase, and one of the effects of ionizing radiation is you ionize water in cells. It's one of it's a significant effect. It's not the major reason for DNA damage, which is what causes radiation sickness and causes cancer based on radiation. But it does do some level of oxidation of DNA and damage. And higher levels of catalase will deal with those, because people who do high levels of aerobic exercise, when they stop, the pathways still keep going a bit, and they end up with a bunch of free radicals floating around that are highly charged that want to attack other things in the cell. So those have to be quenched. So do you want me to continue?
Well, just hold on for a minute. First of all, I'd just like to help make something clear, because you've heard a lot of units. For instance, the earlier discussion was in sieverts and REMs, and Brian's been talking in gray. So gray is kind of like a sievert, except it's the amount of energy, but you multiply it by a quality factor, which can be between 1 and 20 to get the dose in sieverts, because some kinds of radiation have a bigger biological effect than others. But what that means is that a gray might be a sievert, or it could be 20 sieverts, or let's say typically it might be 5 sieverts. So if somebody is getting a gray a day of radiation treatment, such as some of the doses that Brian's been talking about, that's like getting maybe several sieverts a day, okay? That's a lot. What we're talking about here, okay, 0.6 sieverts for the entire round trip, okay? Or that's 60 rem, or maybe 5 rem a month. So I just wanted to put that to allow people to put these different kinds of units against each other. And returning to this issue of the linear hypothesis, a very good analog for this discussion. I mean, the wine is one, but perhaps it's a bit spacious. But one that is closer to this issue is perhaps ultraviolet. Where it's certainly the case that if you get massive doses of ultraviolet radiation, it increases your chance of skin cancer. But if you have 0 doses of ultraviolet radiation, as if you avoid sunlight completely, does that improve your health? The opposite is true. So clearly, a certain moderate amount of ultraviolet is actually desired by the body. And now with radiation, we don't have as much data here, and it's harder to lay this out. But there's actually a significant body of evidence, and the regulators hate it, which shows that small amounts of radiation reduces cancer incidence. Okay, now, I'm not sure that small in this case is the sorts of 5 rem a dose, 5 rem a month rates that RAD measured. It may be lower than that. But still, once again, it makes the linear hypothesis suspect. The other thing that I'd like to point out is this, is even if one accepts the NASA interpretation of a 3% risk, which in my view is not, it's not in agreement with the BAR report, which itself is very conservative. When you flew on the shuttle, statistically you had a 2% chance of being blown to pieces. Okay, that is, they had 135 flights, 2 of them were destroyed. And yet, knowing that, I believe that a tremendous number of people, including all astronauts and many other people who would love to be astronauts if they could, would jump at a chance to fly on the shuttle if they had the opportunity. Now, a Mars mission, we're going to try to make the Mars mission as safe as we can. But the Mars mission is intrinsically much more complex than a shuttle mission. It involves launch to orbit, as a shuttle mission does, but then trans-Mars injection, trans-Mars cruise, entry and capture in Mars orbit, landing on Mars, ascent from Mars, trans-Earth injection, Earth entry, and landing, as well as operations on the surface of Mars. So there's many elements of hazard along that entire chain. And even if we assign a 1% risk to each of them instead of the 2 that was on the shuttle, you're looking at 10% risk. Some of these other things are frankly likely to be more risky than shuttle flights because the shuttle was done repeatedly. They had a chance to learn and correct weaknesses, whereas the first Mars mission will be the first Mars mission. And so it's extremely improbable that a UN Mars mission can be mounted with less than 10% risk of failure due to failure of flight systems or flight operations, and more likely 20% risk. So whether you talk about whether these RAD results represent a 3% risk or a 1% risk, okay, they represent a modest portion of overall mission risk.
Or less.
Okay.
Bob, let me interject a moment.
Sure.
So I think the original charter for this panel was to talk about the significance of the RAD results.
Go ahead.
And I think the significance of the RAD results, first of all, we're only discussing a small fraction of the RAD results, partly because the surface results we've been observing on the surface of Mars for a year, but those results are embargoed because we're trying to get them published in Science magazine. That will happen. And this time
when do you expect publication?
I'd hope in the next 2 months. It's hard
Great.
to know.
Okay.
It's one of those things you never really know.
Mm-hmm.
But I'd love to decide. I was hoping it'd be in press now, and we'd be able to discuss it fully now, because that's really what RAD was designed to do. RAD was designed to make the first ever measurements on the surface of Mars. We've never done that before. We've never made measurements of the radiation environment on the surface of another planet before. That's what RAD was designed to do. During cruise, we had an opportunity to take measurements. They're different from the Marie measurements in the sense that we are inside the spacecraft, so we were shielded in a way that is perhaps not so different than the space station is shielded, perhaps less shielded than a human crewed mission, because the goal would be to make it as uniform as possible. But so the results I spoke about this morning and that I've been able to talk about today have been primarily these cruise observations, which have been kind of a bonus from the mission. They weren't the objective. They weren't the final goal of flying RAD on MSL. The primary objective of flying RAD on MSL is to make measurements on the surface of Mars. And that's working great, and I'm looking forward to being able to share all of that with you soon. But these cruise observations were interesting because what you see and what we found is different than Marie in the sense that we were inside a shielded environment, and yet we still had these dose rates. The other thing that RAD, the importance is, as you were talking about gray and the difference between gray and sieverts, the conversion, as you said, Bob, the conversion from gray to sieverts requires a quality factor which depends on energy and particle type. And so, the beauty of RAD is that it also measures this full spectrum of radiation so that you can apply independently for each energy spectra the right quality factor to characterize this. And the radiation environment in deep space is different than that on the space station in terms of the type of radiation. It's very different than on the Earth from Fukushima or from many other types of disasters. If you have a proton radiation field, the quality factor is 1. And so if you have 1 gray, you also have 1 sievert. But if you have iron, an iron event, that quality factor could be 20, and so you'd have 20 sieverts per gray of iron. So I think this, going back to it, and it's a little difficult to fully appreciate the full significance of the RAD results because I haven't been able to discuss them fully. But fundamentally, there's 2 things that I think are important. You've talked about NASA's policy a little bit. I actually think we're making progress, that actually RAD is a success story for NASA in the sense that the human exploration side of NASA and the science side of NASA are now working together, and it's become the first in a series. And the Mars 2020 is going to be a collaboration between human exploration and science, and I think more and more that's a positive thing. I also think that the RAD results have brought to the attention, to the forefront, even though I think 47 out of the 50 news reports of our science paper were misdirected. As you noted, it brought the subject to the forefront, and NASA fully realizes. I spoke with Rich Williams, who's the chief medical officer at NASA headquarters. I spoke with him this afternoon, and NASA fully realizes that the dilemma of their policies, and but NASA continually reevaluates their policies every several years, and they're in the process of doing that now as we speak. But we now have these measurements that hopefully we'll be continuing to make these measurements over time. They're actually ground truth measurements which one can use to compare with models, and it's great that you had predictions from your from your book and in the past, and it may sound like a variation of a factor of 2 is not so much. That's comforting that it's only a factor of 2, that it's not a factor of 10, but it's important when you're trying to design shielding for that, because every gram and kilogram.
The difference between 58 and 66 is not a factor of 2.
No, but I don't want to get into comparing the numbers. But
Okay.
my point is that it's important to make ground truth measurements. That's the way physics is done. So I think that's the significance of RAD, and I think that I think understanding these measurements, comparing the models with the Marie data, with the RAD data during cruise, and then ultimately on the surface, making resolution of all these and wrapping our arms around them so that not only can agencies like NASA, but private companies make their evaluations. I think and the fact that we're sitting here talking about it today, I think that's the significance and the importance of it.
Well, sure. Let me ask you to clarify a few things. Not too long after Curiosity landed, there were some RAD measurements released on the internet. And they showed or reported dose rates on the surface roughly a factor of 2 lower than that of interplanetary cruise. Could you comment on that?
Sure, that's easy to understand. On the surface of a planet, you only have a 2 pi steradian field of view in the sky. When you're in deep space, you have 4 pi steradian. You can have radiation coming from every direction. So, to zero order, the simplest approximation would be that when you're on the surface of a barren planet like the moon, or that has absolutely 0 atmosphere whatsoever, you would have 50% nominally without having albedo particles, protons, neutrons contributing to your dose. You would logically have about 50% of what you would have in deep space. The measurements on RAD are not exactly a factor of 2 less, but they're not 10%, and they're not 90%. They're in that range. But it's good to know that, and I think some of the more interesting results will come out when we talk about the energetic particle spectra. What's the contribution from the albedo neutrons? I think the neutron environment on the surface was one of the contributions that was less well known because it's purely dependent on models and the regolith and things like this. But those are things that we're working through, and I think that's going to be where the greatest contributions from RAD will come.
So the neutrons are being separately measured?
Correct.
Okay, yeah, good. I was wondering, I was going to ask that question, because
So
biologically, neutrons can have anywhere from 2 to 20 times the biological effect
Absolutely. The quality
after
effect.
being absorbed that photons or that any other type of radiation does.
Yeah, so the power of RAD is that it's a combination of two types of particle detectors. A charged particle detector that characterizes protons all the way up to iron, energy spectra of protons all the way up to iron. That's the traditional charged particle detector, but then also a neutron and gamma ray detector that gets spectra from a few MeV up to 100 MeV of neutrons.
Okay.
Are there questions from the audience? All right, in the red shirt over here.
Hi, I've heard a lot of discussion about solar protons, but what about X-rays coming from a solar flare? How would those affect emission?
Well, the main content of the solar flare, the main threat, is from the protons. And some of them can have higher energies, but most of them have energies on the order of millions of volts. And that can be stopped by 5 inches or 12 centimeters of water, which is available to a crew of a Mars mission because they'll have that much in the way of supplies that if they pack it in around a limited area of the ship, it calls a solar flare storm shelter, and you could go in there and become safe from the solar flare. And that is what makes the cosmic rays of greater importance because they have gigavolts, billion volts, and you can't stop that with 5 inches of water. You're going to get that dose. And but once again, that's not a sudden dose. It's just a pitter-patter of radiation coming in a little bit at a time, extended over a period. And so you don't expect to see any immediate effects of that, which you could in principle get from a solar flare if you were unshielded. You could get 1,000 rem from a solar flare, and that would cause radiation sickness and death during the mission. Donna, I was wondering if you could jump in here on this. With a solar flare, okay, that might deliver 1,000 rems, over what period of time is that 1,000 rems? Is it delivered over a minute, an hour, 4 hours, what?
Yeah, typically, so a solar particle event would last on the order of hours to days, typically days. The events we observed during cruise lasted anywhere from 2 to 5 days. Sometimes it would be a recurring event. It would be a double event. On the surface, we saw one event, and it lasted, the results on the surface were only 1 day. But it's highly variable, both in intensity, as Bob said, but also in duration.
So that if the ship was instrumented even just to know that a solar particle event had begun, even if the crew was out of shielding at that moment, so long as they promptly got into shielding, they'd only get a small fraction of those 1,000 rems.
That's right. I think that it's going to be essential to be able to do your own monitoring and space weather monitoring and be able to know when an event is happening. Also, if you could predict it, that would be even better. But I think the biggest risk would be during cruise if you're not in an optimal situation. Although you would hope the mission design would take care of those issues. But if you're out on a walk, a Mars walk, and a very hard event, meaning a very highly energetic event occurred, and you were not aware of it, and you were caught in your spacesuit, there's potential for problems.
Yeah. I'd just like to add that my talk and the primary focus of the book is treatment methods. There's a lot that can be done, and something I would really like to be able to work on if I could would be trying to save higher mammals that have been exposed to, say, 10 gray or LD 100 doses. I think it's doable today, and I can't get into all that now, but that's what I wanted to communicate primarily in the book.
In the lime shirt, yes, sir. Well.
Radiation in the RAD on Curiosity inside the space container. Did you account in any way for the fact that if you had astronauts there, they would avoid the heavy solar flares, and therefore you wouldn't necessarily count those heavy solar flares as part of the RADs that were received, would you?
Well, RAD is inside the spacecraft, and anything, when a solar flare occurs, when there's a solar particle event, it's pretty much isotropic around the entire spacecraft, and it penetrates through the spacecraft. So, that would be the design. That would be a goal. There is some shielding on, on space station, for example. They have polyethylene sheets that they can go into a compartment and use in the case of a large solar particle event. That would be part of an essential mission design on a crewed mission. These are just the measurements inside the current shielding. It's a measurement. It's not a mission design. It's a measurement.
Okay. I just want to interject one thing here. On the surface of Mars, there is, of course, an atmosphere, and as you mentioned during your talk, looking straight up to the zenith is 16 grams per square centimeter, which is kind of like 16 centimeters of water between you and the zenith. Okay. However, one calculation that Ben Clark did was looking at the average shielding over the 2 pi steradians of the sky, given that most particles are not going to come straight down at you from the zenith, but they will come in every which way, including at an oblique angle through the atmosphere. And his calculation was that the average over the 2 pi steradians of the sky of the atmospheric shielding was equal to 65 grams per square centimeter. Now, if that is correct, then one would suspect that on the surface of Mars, you're quite well shielded against the solar particles. Okay, I'm going to be very interested to see your results vis-a-vis solar particle events on the surface of Mars.
Yeah, I can't comment on that math, but
yeah.
I mean, it's a slab. You deal with it as a slab, and a slab which is of a thickness of 16 grams per centimeter squared. And when you calculate the total dose from a slab that has 2 pi steradian field of view, you calculate the cosine theta angle for the directionality of the radiation.
Well, no, if you're on the surface.
No, but the radiation comes from any direction, and
That's right.
Theta. So that's
Yes.
part of the calculation.
Right, but it's more than 16 grams in that case.
Well, that's the way it's characterized as 16 grams vertical.
16 grams vertical is what you get if you simply take the pressure of Mars and you take the integration of rho g is the pressure.
Sideways in the horizon.
Anyway, let's get more from the audience. Over there, the person who got left out.
Airline pilots are typically exposed to cosmic rays over long periods of time, in many cases years. Has a study been done of airline pilots where there's increased cancer risk? And if so, can that be extrapolated for a crewed mission to Mars?
No, that's a very interesting question. So the polar routes are the most problematic. That's where the magnetic field converges, and so you have the least magnetic shielding on Earth. So when you have a New York to Tokyo route, you're going right over the poles. All the airlines are aware of this. The European Space Agency actually treats their pilots as radiation workers, and they're required to wear dosimeters. The U.S. does not have that requirement, but I think the airlines are aware of it. I do believe that all the airlines subscribe to the alerts from the Space Weather Prediction Center here in Boulder, so that when there is a solar storm or space weather event, I think that most of the airlines try to fly lower latitude routes and don't go directly over the poles. But that's a very astute question.
I can make a quick comment here.
There's thousands of pilots and some very large group that's been flying for decades.
I don't know the study you're asking for. I haven't seen anything like that. What I can say is that a million miles in jet aircraft is worth about 0.011 gray of exposure. So the dose rate is very low, and I doubt you would see anything from that.
Sir, yes, you with the Mac.
Dr. Zubrin, you were recently on the space show talking about this very issue, and I believe you made the comment, something along the lines of all the risks that need to be mitigated for a human spaceflight mission, there were scarier things than radiation. Where exactly does radiation fall on the scale of risks for human spaceflight?
It's one of the smallest of the risks that anybody cares to name. I mean, the real risk, I mean, you're taking off from the Earth here in a lightweight structures that are packed to the gills with liquid high explosive, okay? And and you're going at tremendous velocities, and you're hitting, you know, the Martian atmosphere at velocities of 6 kilometers a second, and you're going to come back, you're going to hit the Earth's atmosphere at 12 kilometers a second, you know, which is whatever, like Mach 36. And then you're doing an entry and landing on Mars, which is intrinsically hazardous. Every time we send a robotic mission to there, everybody's holding their breath, and you know, I mean, you see how it was when Curiosity landed. And, wow, we did it. And then you're doing operations on Mars where things could go wrong. I mean, you know, anything could happen. And then there's the life support system, which has got to be reliable for 2.5 years. Now we can multiply back it up, and we will. But even so, what if, you know, the thing gums up and fails? There's, you know, what if, you know, the software has bugs in it? I mean, so there's all kinds of flight risk, of risk of failure of life support systems, accidents. I view all these things as a more serious concern. And I mean, and so, for example, so much so that, okay, in Mars Direct and also in the Design Reference Mission, the Design Reference Mission 3, which is the one that I had something to do with, we use 6-month transits for the crew out to Mars, okay? Now, why is that? Well, one reason is that, okay, the home and transfer minimum energy is 8.5 months, but if you pour on just a little bit of extra fuel, you can cut it down to 6, and it doesn't cost you that much. If you try to push it much shorter than that, then you really start going up on the exponential, and it's hurting you, okay? So 6 is a nice number. But in fact, 6 is exactly the right answer, not approximately the right answer, because the 6-month transit out to Mars is also the orbit that if you decide to abort, you fly past Mars, you go out to about 2 AU, and you come back and you reach Earth's orbit at exactly 2 years after you left, and therefore the Earth is there to meet you. That's the free return. So therefore, even if I had a superior propulsion system to chemical, like say nuclear thermal rockets, that might make it practical to do 5-month or 4-month transits, I would still do the 6-month transit and use the superior propulsion capability to greatly increase the payload and make my life support system and all other critical systems, you know, quintuply redundant. In other words, rather than try to reduce this radiation dose by 15% and cut this 66 REMS down to 51 REMS, okay, I'd much rather double my life support system as a far better way to assure the safety of the crew. And so the fixation on flight time is actually detrimental to crew safety, okay? Because it takes a great deal to get it much less than that, and you would do much better off backing up the systems which your life really depends on. Okay. up here.
Yeah, hi. Have an interest in cosmic rays myself, and one of the things I remember early in the space program was reports by astronauts, some of the first ones in low Earth orbit, reporting the observation of flashes of light, which presumably was caused by the primary cosmic rays impinging upon the retinas of their eyes. And I just still wonder, you've given us a lot of numbers about dosages and things like that, whether or not, along the lines of the question before the last, has there been any biological experimentation done, maybe around high energy particle accelerators with biological units, to see whether or not there's some extra lethality associated with these very, very high energy particles?
That type of research is ongoing and has been ongoing for quite some time. Typically, we use laboratory animals, and this is how we determine these quality factors. For example, we use different types of radiation and different energies of radiation, and to try to determine how effective they are on all different types of tissues, whether it be ocular tissues or deep tissues or skin tissues. So there's a description of the type of dose depending upon the type of tissue that's affected. That's just the surface of it, but the short answer is yes, and it's actually quite a mature field and area of expertise, and I don't know if you'd like to add anything to that.
Nope.
I would like to add just one thing on that, is that while the cosmic ray radiation dose at the International Space Station, or in low Earth orbit, is lower than that in interplanetary space by about a factor of 2, okay, it is of the same kind. Okay, that is to say, the astronauts in low Earth orbit do experience this kind of radiation because the Earth's magnetic field is too weak to block most of that out. Most of the reduction in dose is due to the presence of the Earth, which blocks out half the sky. Okay, so there are astronauts and cosmonauts who have cumulative time on board the space station or the Mir exceeding 700 days, okay, which is comparable to over 300 days in interplanetary space of cosmic ray doses, and there are no radiological fatalities among this group. None. It looks like, well, we're going to have time for one quick last question. No, sir, I'm going to go get one more person in because we're going to have to end. Over there in the pink shirt. You, miss.
Okay, so I'm riding along in my spaceship, and there's going to be a solar particle incident. I've been checking the space weather. I know it's coming. Do we already have a device that will wake me up out of a sound sleep and tell me to go and get in my shelter?
An alarm clock.
I wouldn't think that would be so difficult to devise, but on the space station, I think the sleeping quarters are the best shielded areas. So you're already in the location that you would be best prepared for. But that's a mission design question, and I'm sure that would be thought of.
All right. So that winds it up. People who have additional questions for Dr. Hessler or me or Brian, just catch us in between sessions when you can. Thank you.